Hello all, welcome to the AI driven perception learning and mapping for drones course. This lecture will focus on learning from sequential data, focusing more on the RNNs and LSTM. In the previous lecture, we focused on the memory network neuron. We saw how every network neuron has a dedicated memory neuron for it, and we also saw the working for the whole input. We also saw the working of the RNN for various layers, the output and the upgrade or the modification of weights based on back propagation through time. Now in this lecture we will focus on other architectures that can learn the sequential tasks and data better, focusing more on RNNs and LSTMs. Now, even in the previous lecture, we have discussed the sequential learning tasks. Some of the fundamental property of sequential learning tasks are that the inputs are not independent. Essentially, since it's a time series data, different timestamps of input are dependent on each other. Some of the examples of this are video data, right? And the input and output length are not always the same. So, it has a variable temporal context. However, the task overall remains the same. An example that we also saw in the previous lecture was the task of text completion, where essentially giving a word like a C followed by every letter, this would upgrade or this would change the input context length, and similarly it would also change the output. Right. However, the task of text completion remains as it is, right, and we want to focus on deep learning models that do this task better, which is the task of sequential learning. We also discussed the feed forward neural network and the recurrent neural network, right. So, in feed forward neural network, the input vector x is independent of the output, and this is observed as once the input is passed, the information propagates in a forward manner, and once we calculate the error, we can update or modify the weights based on back propagation, right. So, there is no sequential relationship between the previous or the past input and output. Now, in recurrent or feedback neural networks, we observe that the output y depends on the current input, which is xt, and the previous output and input, which is highlighted by xt minus 1 and yt minus 1, right. So, as observed in the figure, we have an input which is xt and a corresponding output. However, since we have a z minus 1 block, we are trying the input and output, we essentially use the input and output at t minus 1 timestamps as well, right. Now, feedback neural networks are learning sequential relationship between both the past input and the past output, and it has various applications in trajectory prediction, system identification and so on, right. Now, let us focus on RNNs, which is the recurrent neural networks. As observed traditionally and even throughout the duration of our courses, we have observed that the input and output are essentially independent of each other, right. However, for sequential learning tasks, we need to learn the relationship between the input and the output at various timestamps. This is why the recurrence phenomenon should be learned by the deep learning model, and which is why recurrent neural networks were developed, right. A simple recurrent neural network can be observed in this figure, where we have an input at timestamp t. At that input, for that input, we also have a context or a hidden state. This is something similar to what we observed in the RNN as well, which was highlighted by the memory neuron. We also have the output of this particular network, right, which is again at timestamp t. However, we have a context window or a memory or hidden state which focuses on learning the context or saving the context at t minus 1 stage, right. Now, this is the overall structure of RNN and LSTM, and the context, the neural network that learns this context could vary. However, the overall structure remains the same, where we have an input, we have an output, we have a hidden state, and we have a state which focuses on preserving the previous history of the context as well. Now, let us take a look again at different types of neural networks or different types of recurrent neural networks. Now, RNN, as we observed even in the previous slide, can work with a variable temporal context, which is a variable input output length, right. They could work for different input and output. For example, a one-to-one architecture which has a dedicated input and a dedicated output, and we also observe the hidden state in the middle, right. This could also be a one-to-many where we have one input and multiple outputs. This could be from many to one and many to many. Some of the examples of one-to-one are where we have an image and we want to generate a caption for the image, right. So, we would have a text description for an image, and this text description can vary according to the image, right, which is why the temporal context of the output could be variable. Similarly, we can have a many to one scenario where we can pass in a video, which would essentially be a recurring, we could pass a video which is a collection of frames, and we could essentially label it for a given particular action. So, we can have videos and we can classify it for a particular action. We can also have many to many relationship where we pass an input video and it generates an output text, right. And in this particular scenario, the temporal context of both the input and the output keeps changing. However, the task remains the same, which could be video captioning for a many to many case, right. Now, as observed even in our previous lectures, existing CNN models or existing convolutional based architectures cannot fully appreciate this phenomenon on dealing with variable sequence lengths, right. We have observed that connets take a fixed or they are compatible with a fixed resolution of image, right. So, they do not generalize over inputs with a variable context. Now, let us take a look at RNNs in a more detail. RNNs are essentially follow this structure. RNNs follow this particular structure that we observe on the left, which is it has an input, it is passed through an RNN structure, or we call it as a hidden state, and this hidden state could actually be any neural network that appreciates understanding a sequential data. And once the output of hidden state, it reaches the output y. Okay. Now, at each time step, the input vector is fed into the RNN and it outputs y, right. Now, let us unroll this particular RNN structure. When I say unroll, it means it starts from a stage 0 and in a recurring fashion it grows to an nth stage, right. Now, the unroll RNN could be observed here, where we see an input at the stage x1, which is the state 1. It passes through RNN and generates y1. Similarly, we observe it in other states as well, right. So, x1 generates an output y1, x2 generates a corresponding output y2, and so on, right. And we observe that RNN, which learns the hidden state or the internal state, is linked to it links various inputs and outputs. For example, if we wanted to relate y3 in terms of x1, we can see that using this hidden state we can essentially write y3 in terms of x1, right. This is one of the fundamental features of RNN, where it can help to preserve the long temporal context, right. So even for yt we can learn in terms of x1 and x3. So it relates an output at various temporal layers with corresponding or inputs at previous stages. Now let's write or let's appreciate or let's focus on the recurrence relationship of an RNN, which can be highlighted from the given equation. So this particular structure of RNN could be highlighted by this given equation, which is ht is f uw of ht minus 1 and xt. Here xt is the input at the stage or at the state t, so tth state. ht is the value of the hidden state at the timestamp t. Similarly, ht minus 1 is the hidden state at timestamp t minus 1, right, and u, v and w are the learnable parameters. We will come to v in the next slide. These are learnable parameters. Now as we observe in this particular equation, although there is a recurrence relation between h and x, which is it depends on t and t keeps increasing, right. So we can write h1 as f h0 x1 and then we can write h2 as and so on, right, and it is a recurrent relationship because h1 can again be written in terms of the first equation. However, we observe that the learnable parameters across this network remains the same. So u, v, w, which are the learnable parameters, remain the same throughout the whole unrolled RNN as well. Now again we can write the earlier equation in a different fashion, right. So let us focus on this particular equation. The hidden state ht could be written as a tan, which is the activation function of w times ht minus 1 plus w xh times xt, right. Now once we have the hidden state, which is identified as the output of the RNN, we can also write y, which is the output of this particular RNN at timestamp t, which is given as why times ht, right. Now if we want to write the same in this particular rolled RNN state, we could write that using the input x we need to pass it through wxh. For the internal state the weights are whh and the output weights are identified as hy, and we can also follow a different nomenclature where we, for simplicity, we can just write it as v, w and u. Now let us look at an example to appreciate this better, right. Let us look at an example where we have an RNN structure. Our goal is, given a sequence of characters in a word, we want to highlight what would be the next letter, right. So essentially the goal is we want a character level prediction for the word hello. So for every input the RNN structure should predict the next letter in the word hello, right. Now let us look at this from an example point of view. We can write the hidden state as ht, which is tan of w times h t minus 1 plus w times xt, right. Now let us follow a one hot encoding structure where h, e, l, o are represented as a one hot encoding. When I say one hot encoding, it means in a vector only one part of it is 1 and the rest of the parts are 0. So if we have a vector where we want to highlight h, we can write it as 1 0 0 0. Similarly e could be represented as 0 1 0 0, right, and similarly for l and similarly for o. Now this is just an encoding for simplicity, right. Once we have this encoding, we can write the hidden state, which is ht, which is given as tan h of whh times the previous timestamp. Let's assume we do not, okay, let's assume we have a previous timestamp plus WXH times 1000, right. Now once we write this equation, we know that HT as observed in this figure would be 0.3 minus 0.1, 0.9, right. And once we have the hidden state, we can use the equation we saw in the previous slide, where y is a function of this, and we can have an output prediction of this particular RNN state, right. Now once we have this output prediction, we can, for the letter E, we can follow the same structure. However, for letter E, so this was for H, this is for E, which can be given as tan H of WHH. HT minus 1 would be the previous state, right, and this is the HT we get for the letter E. Once we have this hidden state, using the previous formula, using the same formula we saw earlier, we can have an output prediction of Y, right, and this can go on, right. Now once we have a dedicated output, we can calculate the loss and we can update all the learnable parameters here, right. Now again, in this particular example, we do not have the exact value of W or the dedicated weights. This is just to understand as an example how the propagation would work, where once we have a hidden state, when we pass an input E, we take the previous hidden state, we take the input, multiply it with corresponding weights and generate the hidden state for the layer which is HTE, and then we generate the corresponding output, right. Now again, RNNs have different, could be used in different applications as well. It could be used for machine translation, where we want to translate from German language to an English language. So the input is a sentence in German, and using the RNN structure where we calculate the hidden state and then we calculate the output, we can generate the English statement as well. This could also be done in a image context, where we pass in an image and it has to generate descriptions for each of the objects in the image, right. So RNN structure, which works with various hidden states, could be used across a lot of different applications. That could be for prediction of sentences, it could be for machine translation, as well as for sophisticated tasks like image generation, right. Now again, let us take a look at the RNN structure and let us try to focus on the backpropagation algorithm, right. Now we focus on the for the rolled RNN structure on the left, we observe that we have an input X, we have the hidden state S, and we have the output which could be O or which could be Y cap, right. Now again, this is similar to the example we saw earlier with a minor change in notation. So please do take care. There is a change in notations. Change in notations is merely with respect to the learnable weights, right. So we have U, W and V. Now once we unroll it, it is, or unfold it, we are trying to generate the structure of RNN for each timestamp, right. So for t is equals to t minus 1 to t plus 1. For each of these timestamps, how does the RNN flow? Now we can observe it in this figure, where we have W, which are the learnable weights for the hidden state. We can also see U, which is focused on the learnable parameters for the input, and V, which is for the output, right. Now again, this is a very similar structure we saw in the previous slide. Let us look at the equations where we define ST, which is the hidden state. This hidden state can be represented in a similar manner we saw even in the previous example, which is tan H of U xt plus W st minus 1, right. We can write the output prediction yt cap right, as softmax of V into ST. Now each timestamp would have their dedicated output prediction, and for each of these output predictions we can compute the loss because we have the ground truth for each of the timestamps. Now again, one point that we observe here is that all the parameters across different stages, as observed in the figure as well, are shared. So we have a common W across hidden states, we have a common U across different input for different timestamps, and even we have V which is common across output predictions, right. Now let's focus on the backpropagation through time. We call it backpropagation through time because the learnable parameters are shared across all the timestamps, right, and we want to learn or we want to find the best possible parameters which is UVW, so that the total loss across the training data could be minimized. We call it backpropagation through time because as we observe, UVW are shared across various timestamps. So as we are backpropagating, the backpropagation depends upon previous timestamps as well, right. Now let us say YT is the ground truth at time t and YT cap is the output prediction. We can write the cross entropy loss used for each of the timestamps t as ET. Now ET is given as minus YT log YT cap, and since we are focusing on all the timestamps, it would be a summation of T ET. So it is a summation of error across all timestamps, right. Now let's focus on this particular structure which is similar to what we saw earlier. We have the learnable weights W, right, which is the learnable weights for each hidden layer. We have U and we have V, right. Now each RNN at various timestamps would have an error, right, which is why the error is defined as E0 plus E1 plus E2 and so on, right. Now we can, using the RNN equation, we can write the output prediction which is Y1 cap, Y2 cap and so on at each of these timestamps, and we can also write ST which is the hidden state which is S0, S1, S2 and so on for each of these timestamps, right. Now our goal using the our goal here is we want to calculate the gradients, which is we want to calculate the most optimal set of learnable parameters, and we can do it in a similar manner that we did even in the previous lecture, which is theta star is equals to arg minimum theta E theta. Essentially what we are doing is we have the error, but now the error is an error across all the timestamps, right. This error is what we want to minimize, and we can do that using our gradient descent algorithm. When we minimize, which is arg minimum of E theta, we get theta star which is the optimal set of learnable parameters, which would be U star, V star, W star, right. Now again we call it backpropagation through time because these set of learnable parameters are same across different states, and we will observe this in the next slide that as we backpropagate through even previous timestamps to get the most optimal set of UVW, right. Now let us take a look at deriving or the error propagation using the chain rule to update various weights at various levels, right. So as observed in the figure, let us focus on E3, right. It is just an example, we can do it for other time series as well, timestamps as well, right. Now for E3 we know W is the learnable weights for the hidden state, we know V is the learnable weights for output, and similarly we know U which is the learnable weights for X3 which is the input, right. And again they are similar across the other timestamps as well. Now when we are deriving or when we are focusing on dou E by dou V, right, because essentially we need to minimize the error and to use stochastic gradient or to gradient descent, we want to calculate this particular derivative. When we are doing that, we observe that V only depends on the current timestamp, right. So it depends on E3 and S3 only, it does not really depend on anything else. So when we are focusing on error propagation, which is dou E3 by dou V, we using chain rule, we can break it into dou E by dou Y3 cap times dou Y3 caps upon dou V. Now if we observe this equation, which is dou E3 by dou V, it only focuses on the elements which are in the current timestamps, it does not focus on any other elements, right. Once we use the chain rule to break dou E3 by dou V, we can break it further. So dou E3 by dou V could be written as dou E3 by dou Y3 cap times dou Y3 caps by dou Z3 and dou Z3 by dou V. Now Z3 can be written as V times S3, right. Now once we solve this equation, we would get the final form, which is dou E3 by dou V could be written as Y3 cap minus Y3 into S3, right, and this is essentially using the chain rule itself, which is something we have seen even in our multi-layer perceptron, right. Now what we observe here is that dou E3 by dou V can be written in a very simple equation, and if we observe, all of these elements depend on the current timestamp, right, and it is also intuitive from the graph as well. The learnable parameter V connects only the layers which are learnable in that timestamp, right, and similarly if we calculate dou E4 by dou V, you could also have a similar equation, but all of the elements in this would focus only on that particular timestamp, right. Now the learnable parameters we have is V, U and W, right. Let us take a look at W. Now as we observe in W, we see that even for E3, or if we wanted to calculate dou E3 by dou W, we observe that once we reach W, it has a recurring relationship, right. So when we are using a chain rule, we observe that W has dependence on S3, which again has dependence on S2 and so on, right. Now let us look at the error propagation, which is dou E3 by dou W, right, and using the chain rule we can break it into dou E3 by dou Y3 cap, dou Y3 cap by dou S3, dou S3 by dou W, right. Now let us look at the last term. Now the equation of the hidden state ST is given in this particular equation. If we wanted to write S1, it can be written as tan H of Ux1 plus Ws0. S2 could be written as tan H of Ux2 plus Ws1, and S3 can be written as tan H of Ux2 plus Ws, right. Now when we observe the last term, which is dou S3 by dou W, when we are trying to take the derivative of the last term, we observe that W depends on S2 and S2 again depends on S1 and S1 again depends on S0, right. Now as we observe, this is a recurrent relation, right, because once we write S3, it could be written as a very complicated term and so on, right. So based on this, which is a recurrent relationship, we can modify this particular part as, so dou E3 by dou Y, dou E3 by dou W can be written as dou E3 by dou Y3 cap, dou Y3 cap by dou S3 and dou S3 by dou W. Now as we observe, this last term is a recurrent term because S3 depends on S2, which depends on S1, which depends on S0, right. So we can write dou E3 by dou Y as a summation from k is equals to 0 to 3. The other terms remain the same. The last term is modified as dou S3 by dou Sk, dou Sk by dou W, right. Now if we want to visualize the same thing even in the figure, what we observe is that when we are taking the error E3 with respect to S3, right, but since we have a recurrent relationship, this particular equation as observed in the figure has a chain ruled reaction, which is dou E3 by dou W will then depend upon this gradient, which is dou S3 by dou S2, dou S2 by dou S1 and dou S1 by dou S0, right. Now as we have discussed even in the previous lectures, we observe a phenomenon of vanishing gradient problem. This is something we discussed even in the ResNets and even for activation functions as well. When we look at the derivation of dou E3 by dou W, right, we know it depends upon these derivatives, right, and we also know that S can be written as tan H U x t plus W S t minus 1, right. So we know that each of the hidden state depends upon tan as well. So when we keep taking a recurrent derivative, right, of tan H, this is when the vanishing gradient problems comes into picture. If we observe the graph of tan H, we know that after certain values, right, the value of this activation function is very small, right, and since we have a recurrent relationship again and again, which is taking the derivative again and again, we observe that the effects of say E4 or E3 on the weights which is here, which is in the earlier part of the network, is very small, which is essentially the vanishing gradient problem. One another application that we have of RNNs is that of a bidirectional RNN. Now in the previous lecture we observed that in the previous slides we observed that the dependence on the current state, which is say Yt or Ht, depends only on the previous states, right, but we could also have a bidirectional RNN, which is essentially two RNNs stacked on top of each other. Now what happens here is that the RNN depends upon the previous hidden state, which is the previous history and the future states as well. This can be observed in this particular figure, where let us say we take the hidden state 0, 1, 2, 3. For the hidden state 1, we observe that for the state 1, we observe that for the hidden state it depends upon the previous history, which is the previous state at 0, but it also has a recurrent relationship with the future states as well, right. So this is just an example of a bidirectional RNN where even the future states could be used to influence the current state. Okay. Now we have observed the long term dependency problem of RNN, right, and this is something that we observe using the vanishing gradient problem. Now RNNs is essentially when we have a rolled in version, and when we unroll it we can see its effect of different stages, right. Okay, there is again a change in notation, so please do take care. We have x0 which is the input and we have h0 which is the output for this particular RNN, right. Now as we observed even in the vanishing gradient problem, when we are observing the hidden state or the RNN as ht, right, we observe that the influence of the states, which is x0 and x1, there is a long distance here, right. Now due to the influence of vanishing gradient problems, we see that the influence of these earlier inputs on the timestamp or on the hidden state of t is very less, right, and hence RNN as a structure do suffer when they are dealing with a long range of temporal context, which is the input at time t would have an issue regarding updates or respecting or learning from x0 and x1. Now RNNs, which is observed on the left, can also be written or can be shown with the figure on the right. We observe that there is an input, there is a corresponding output, right, and we observe the tan h here, right, because we wrote st, which is the hidden state, and we wrote the output yt in the previous slides, right. So we know st depends upon tan h, and we can observe this relationship in this particular fashion. Okay. Now let us discuss LSTMs. LSTMs are fundamentally more comfortable with dealing with a temporal context which is large in nature, which is something that the RNNs do not deal with naturally, right. Now LSTMs are designed to focus more on long term dependency problems, right. It is because it has a repeating structure, and more importantly, compared to the RNN structure we saw earlier, there are 4 learnable gates or cell layers compared to only 1 layer in RNN, right. Now in LSTM we have 1 cell and we have 3 gates, right, and all of them together have a work in such a manner that it helps retain or forget information, right. So let us take a look at all of these gates. The first gate is the cell gate. Now if we observe the figure, which is the first part of the figure, right, the cell gate takes the information from the previous state, which is c t minus 1, and it connects to the current state, which is ct, right. Now cell state are essentially just a gateway mechanism to connect the old cell information to the new cell information, right. However, it does have influence with respect to the other gates, right. Now in LSTM, based on the figure, let us clarify. xt is the current input, ht could be defined as the output or the hidden state, right, and we have ct, which is the cell state. Cell state is essentially useful to retain or understand the information in previous timestamps, right. Now let us look at how the information could be learned or modified using different gates in the cell state. The first gate that we observe is the forget gate. Now as the name suggests, forget gate is essentially trying to take the forget gate takes the input of xt and ht minus 1, right, using a learnable weight and a corresponding bias, followed by a sigmoid operation. This is essentially ft. Now ft, if it is 0, it means forget the information, and if ft is 1, it means that retain all the information, and somewhere in the middle is essentially a mix of forgetting and retaining, right. Now as observed here, the forget gate multiplies to the previous cell information. Let us look at the input gates. The input gates are essential because they focus on defining a new candidate cell, which is different from the previous cell of the previous state. It is defined as sigma of w times the ht minus 1 and xt, right, and the new candidate cell, which is c cap t, can be observed in this equation, which is the tan activation function of this particular quantity. Now once we have it and once we have the new cell candidate, essentially both of them are multiplied and added to the cell gate. Now we also have the input gate. the input gate focuses on merging the information from the forget gate and the input gate, right. So, the cell information from the previous state cell state t minus 1 to the new cell state t can be forgotten using ft and could be modified with new information using the input gate, right. So, Ct, which is the current cell state, can be written as ft times Ct minus 1 plus it times the new candidate cell. Now, the final layer, which is the final output and the hidden state, can be observed as OT, which is defined here, and finally we define HT, which is OT times tan H of the cell state, right. Now, this is the summary of various layers. This is the summary of different states of LSTM. So, as discussed, we have a cell state and we have a previous cell state and a new cell state at Ct. We have a forget gate which essentially takes an input from the previous hidden state and the current input, and it tries to focus on what to forget in the previous cell state. We also have the new input gate and the candidate cell structure, which essentially adds information of the new candidate cell to the previous cell state, and finally we have Ct, which is the modified version of the new cell state. Once we have Ct, we have the new hidden state and the output Ht, right. Now, there are different variants of LSTMs as well. One variant we observe here is the LSTM with peephole architecture. If we observe in the previous structure for the input and the forget gates, it dependent only on the hidden states, of which is Ht minus 1 and the current input, which is Xt. However, for the LSTM with peephole architecture, it is essentially peeking into the cell state, which is involving Ct minus 1 here, right, in all of these gates. And we also have architectures like gated recurrent new unit, which is essentially the GRU block. GRU block is a simplification of LSTMs where the forget gate and the input gate are merged, and where the hidden state and the cell state are merged, right. So, the architecture of GRU can be observed here, which is essentially trying to simplify the number of gates and the number of hidden states. So, to summarize, in this lecture we covered the temporal data, what are different sequential tasks that could be there. We also went into a detailed study of RNNs, so the applications of RNNs, the structure of RNNs, the unrolling of RNNs, and the backpropagation through times for RNNs. Now, RNNs observe the vanishing gradient problem for data which has a very large gap in their input timestamps, right, and hence there are structures like LSTM that focus on dealing comfortably with this issue. We observe the structure of LSTMs, we also observe the different variants of LSTMs, which is the LSTM with peephole architecture and the gate GRU block. Thank you.